Okay, so we talked about the direction of the force only. Now we had a wire going through the poles of a magnet, uh, felt a force, and we only discussed about the direction of this force. We never talked about the magnitude of this force, and that's what we are going to talk about now. Well, that's the equation. Okay, this is the equation that tells us what is the value of the magnitude of the force. What does it depend on? It depends on I. I is the current that is going through the wire. Yeah, so this is the force on the wire. It depends on the current going through this wire. Depends on L. This L is the size, is the length of the wire, but only the length, the piece that is between the poles, okay, that is in that magnetic field, not the whole wire necessarily, only that piece that is inside. Now, so in this drawing here, we only think about this piece here, which is inside between the north and south pole, not the whole length. Okay. So depends on L, depends also on the magnetic field. The bigger the magnetic field, the bigger this force will be. Okay, and there is one more thing in this story, which is this theta. This theta is the angle, so sine of theta. The angle of what? The angle between the direction of the current and the direction of the magnetic field. What we had before, in all of those examples that I told you before, the current and the magnetic field were perpendicular. Perpendicular means field 90 degrees. No, sorry, angle 90 degrees. So sine of 90 degrees, 1. Okay, so when the current and the magnetic field are perpendicular, we get the largest possible value for that force. If the current and the magnetic field are in the same direction, this is important, okay? If the current and the magnetic field are in the same direction, then the angle between them is 0. And then there is no force, no matter how strong the current and how strong the field is. Okay, so let's say the magnetic field is pointing to the right, okay, as in the example that we had before. When we put the current going into the page, we got a big force on this current, on this wire. But if now, instead of putting it into the page, I would put the current in the same direction of the field, there would be no force. Okay, so going back to that drawing, this is the magnetic field, right, going to the right. If the direction of the wire was also to the right, there would be no force. Okay, we only have this force here and a very strong force because the wire is going is going into the page. Okay, and it's perpendicular to the field, so we get a strong, the strongest kind of force. Okay, so this is the equation for the force. We put here the current. Let's, if we are thinking about international system, we are going to put the current in amp, the length in meters, and how about the field? Well, if we are using the international system, well, what is going to be the unit for the magnetic field? Well, Newton, no, which is international system, divided by amps, divided by meter. That's what you see here. Newton divided by amps and meter. This whole combination here receives a name and it's called Tesla. Okay, so the unit for magnetic field in the international system is Tesla. If you want to use the CGS, gram, centimeters, we also talked about this choice, then the name of the unit for the magnetic field is Gauss, and Gauss is 10 to minus 4 Tesla. Okay, all right, so this is the equation that we have for the magnitude of the force. And you see here this important sentence: maximum and minimum force for that current, for that field, for that length will depend on the angle between the current and the field. If they are perpendicular, we will get the maximum force for those values. If the current and the magnetic field have the same direction, no force, 0. Okay, so let's then just solve this problem. This problem is very simple. It's just putting numbers into the equation. It's just to practice a little bit using this equation. Okay, so what do we have? We have a wire carrying 30 amps. Okay, so let's write this there. We have our current is 30 amps. Has length 12 centimeters between the faces of the magnet, between the poles of the magnet. Now, remember what we said? We only care about that piece of the wire that is between the poles. Okay, so the length is 12 centimeters. Let's convert it to meters. We are using the international system, 0.12. Now the angle between the current and the field, 60 degrees. So the theta is 60 degrees. Okay, this is important. And they tell us more. They say that the magnetic field is approximately 0.9 Tesla. Okay, so now we have everything. We just have to put all that into the equation. So you just put all those values into the equation. Current, length, field, and the sine of 60 degrees. And you're going to get the value of the force, which is 2.8. Okay, the next slide is just to repeat what we already talked a lecture ago, which is this choice of when we want to say that something is going into the page or out of the page. So if we are talking about the magnetic field, if the magnetic field is going into the page, we denote with these crosses, which is like an arrow going into the page. If the magnetic field is coming out of the page, then we denote with these dots. So it's like the tip of the arrow, and here is the tail of the arrow. Okay, so this is enough for this lecture.